Well, this lecture talks about how to use R to estimate a simple binary regression model. In this case, specifically a binary logit model, and provide interpretation for a basic interpretation for the results. So here I'm going to go over basic data management that led to the data here. So here I'm going to run a binary logit. I call that estimation result object my logit, which is equal to GLM. Okay, GLM. Here we use the GLM function. Well, the GLM function actually is from this stats base package that comes with installation of R. Okay, so we're going to specify this binary response variable, mental health C2. So if anyone has any mental health issues, it's going to be coded as 1, otherwise coded as 0. And this variable comes from this mental health, MNTL, HLTH of General Social Survey. So we're going to use a list of covariates, age, female, okay? So female is coded as 1, male is coded as 0, black, other. So these are race dummies, and the white dummy is omitted. So the white white's going to be used as the reference category, right? So for this black variable, the black is coded as black dummy. So black is coded as 1, and all others is coded as 0. For other, other racial categories is coded as 1. Black and white are coded as 0. Education in years, income in $1,000, and the data we specify the data is use DTA, and family, here we're going to use binomial, which denotes binary regression, and the link function is logit. So it's going to estimate a binary logit model. If we're going to use a binary probit model, simply we can specify probit here. So we're going to run this model and then look at the results here. So it ran through the model, right? So first of all is kind of call of the formula, basically kind of recall of what we supplied, right? And we have a couple sections. The first is deviance residuals. Well, deviance residual is kind of residual, okay? And it has pretty complicated formula. And it is to compare our current model to a saturated model. Then, so what is a saturated model? A saturated model is a model which has many coefficients are their observations. So basically, we give each observation like dummy variable, okay, and estimate it. But this is not the key piece of information here, right? Deviance residual. It is basically, kind of model comparison statistic by comparing current model with saturated model. So let's look at the coefficients. That's the main part, okay? So here are estimates, right? A positive estimate means that its corresponding variable has a positive relationship with the binary response variable coded as 1. So for example, female, so its corresponding coefficient is positive. What does that mean? Well, that means being female as opposed to being male is going to increase the odds or increases the likelihood of this binary response variable being 1. What is being 1? Having mental health issues. Right? Education, it's a negative. Well, that means education is negatively associated with this binary response variable, being coded as 1. Okay, so basically, we're going to say, well, as education increases, the likelihood or the probability, roughly speaking, of this response variable being 1 decreases. And we know that using the latent variable approach, basically the binary response variable could be represented by a latent continuous variable from negative infinity to positive infinity. And it represents the propensity or likelihood of this variable, binary response variable being 1. Here, we can also look at statistical significance, right? Standard errors here, z-values, and p-value, right? When the p-value is below the conventional level 0.05, we see they're statistically significant. And these are different levels. Well, people say, what if I want to know more kind of model fit statistics? Well, we can do that. We can certainly do that. So we can kind of call the disk tools package, right? Here, around that. And we can look at a couple of model fit statistics. For example, the pseudo R squares, McFadden R square, Dujoux R square, and AIC. Okay, Akaki information criteria. Right. Well, unlike the R squares in linear regression models, we can simply say, well, there is 2% of variation, explain on 3%, etc. But the larger R squares, the better the model fit in general. But for AIC in general, the smaller the value, the better the model fit. And we can also use the AIC function to directly calculate the AIC for this model. Okay.